currently a third year exchange student here at NTU from IT Bombay. This is a show and tell video for a hands-on project for the MS Systems course that I'm doing here. We'll call it myRio Air Music. The purpose of the project is to create computer-generated sound, or music for that matter, motion controlled by the device provided by National Instruments called myRio over the air. The idea is to utilize the onboard accelerometer to perceive the motion and pass the information to the host, which in this case happens to be a laptop, wirelessly, and where certain computations are performed to produce sound. Let's have a look at the physical setup. This is the myRio device I was talking about. This is my host PC. Both of them are connected to a wireless network hosted by this router. The information exchange happens between these two devices when one of them publishes its information over the network and the other one acquires them. To keep things simple, I only use the x-axis measurements to provide a control for the main sound generation application on the host device. Let's see how all this works. So, let me open Labview first. This is my project, Air Music. As you can see, the application is organized in two parts, one for the host PC and one for the target device. I'll open first the main application on the target device. What this does is it basically captures the X, Y and Z measurements, but only passes certain information to the host PC. I'll show you that, but let's see. This is a waveform chart describing current measurements of the device. You can see how the value changes. Let's see what's happening at the back end of this application. So, the crux of this application is over here. These are the three variables published by this application on the network. And this is the accelerometer which does that. But we need the host application to acquire this data. So I'll go to the main program of my application in host. This is called host main.vi. Yeah. And now I run it. So let me first talk about digital sound synthesis. It is a discipline on itself, and while there are various good ways to do it, what I'm going to do is illustrate three of such ideas. So I've organized my main application in three modes: brute force, Karplus-Strong guitar, and MIDI utilized. So the first mode is very simple. What I'll do is just run it and then explain what's happening over there. So what this method does is it creates harmonics of a given frequency, and suitably combines them to produce good enough sound. In this application, you can see I have used 5 frequencies, 5 harmonics of which are the 5 harmonics of the given frequencies. There's this control handle obtained from the accelerometer. What this shows is the key position on a 102 key piano. Actually, the 180-degree rotation of the myRio device is mapped to these 102 key frequencies. So what is now you can see is the 50th key note which is being played. I'll increase the volume for you to hear it properly. Yeah, I'll show you the operation by rotating this device, how it happens. Yeah, you can see the frequencies are lowered, and you can also see the same in the power spectrum graph in higher frequency ranges. Now frequencies are increasing, the key position is increasing. Here, so this is basically how it works. I'll briefly go over the backend application. So here are the 5 types of waves you are trying to combine. So as we saw here, this was each of the harmonics you can specify which type of wave you want to combine, like square wave or triangular wave, sine wave, sawtooth or square, to generate different kinds of frequencies. So the crux of this application is this, which uses 5 function generators to produce waveforms in real time. The collected waveforms are then displayed in the power spectrum, and a queue of those waveforms which is acquired here is passed on to the sound card to play it. The configuration of the audio playback is done over here. This is where you control the volume, and this is where you write. You suitably open before doing anything and close it over here at the end of the application. Let me go back to my front panel. I'll increase volume. I'll show some certain other controls, and as you can see, most of the frequencies in this range. Let me remove the auto scale and see the major frequencies here. If I make it sine wave, all of them are sine wave, you can have a better look at them. This will be probably very clear to you. You can see the peaks corresponding to this fundamental frequencies. You see, frequency is lowered, the frequency is increased. Okay, so that's it for this application. I'll close this application. Yeah, so we quit now. The second mode of operation which I'm going to illustrate is the method in which I try to simulate the sounds of a guitar. Let me enter the mode. Yeah, so what I do is I have once again mapped the 180-degree rotation of the myRio device to the chords of C major scale. So as you can see, this front panel showing a pop-up in the air. So, corresponding to the rotation, I receive the note number which corresponds to a chord. This also displays the strings in chord, the fret position. Also, let me increase the volume so that you can hear it. Yeah. So this is it. You can see how the chords are being played. So this is a number corresponding to F major chord. So those who might know how to play guitar might know F major chord is usually played in 5 strings, and these are the fret numbers corresponding to each of the strings. This is the sharpest string, this is the thickest string, in that order. So when I rotate the device, I can change the chord. This is the C major chord. This is the, again, a different chord, A major chord. What you can do is here change the strumming rate. Also, if you want to hear the individual strings properly, actually I'm increasing the time between the plucking of each string, so basically I'm decreasing the strumming rate. So let's see what happens when I hit enter. So you can distinctly hear individual strings being plucked and their sound. You can also select whether to strum down or strum up. So if I select this, I can actually hear the sharper strings first and the lower frequencies strings later. So this is down strum, this is up strum. Let's see what's happening at the back of this application here. So the crux of the application lies here in this 6 string emulators. So each of them receives a string offset which is utilized inside this to produce suitable waveforms. So how does this work is, let me go inside here. So the idea is very simple. It's straightforward from the Karplus-Strong algorithm itself. What you have is a sequence of random numbers and you pass it through a IIR filter over here to generate periodic sounds. The important thing is the IIR filter has its poles corresponding to the harmonics or the frequency desired. So it generates a waveform corresponding to a pluck of a string. This Labview code includes a MATLAB script here which is used to compute the coefficients of the IIR filter. Well, this could have been done without invoking MATLAB for this, but it requires another package for the Labview which is not available in this laptop. So the MATLAB script does a very fine job of generating this coefficients. Yeah. So this way is what emulates the plucking of a string. All this plucking of the strings are then combined suitably according to the strumming rate and the strum pattern over here to generate appropriate waveforms. This part of the code is where you provide the random numbers to each of the string plucking emulators. Rest of the things are similar to the brute force synthesis method. The sound configuration and the queue in which the waveforms are passed on to the sound card. Yeah, that's it for this simulation. Close this window. Yeah, a few more strums before I close this. I increase the volume to here and make it down. So this is the C major chord, the D major chord, the E major, the F, the G, the A, and the last the B major chord. Yeah. So now I quit it. Yeah. This is for the Karplus-Strong guitar. Now let's go to the third mode. This third mode of operation is actually not a digital sound synthesis technique in its own right, but it's actually a pretty good way of generating sound using computer, which most of the modern day electrical music instruments utilize it. What happens here is you have a pre-record patches of sounds corresponding to each of the note frequencies, and based on certain events, a sequencer is uses a protocol called MIDI to process this sounds and output it using your sound module. So the essential idea is the MIDI protocol, which the sequencer utilizes. So this is what MIDI utilized mode is illustrating. Actually, this is a code I adopted that is freely available from the Labview's official website, National Instruments official website. So what I've done is slight modification to give it a control handle from the myRio device. Let me enter this mode and let's see it better. Yeah. So let me first operate this using the normal mode it was designed for, that is to respond to the events based on your PC's keyboard. So let me show you how this works. Should hear a sound? Okay, so let me first configure a device here. Let me test this. Yeah, this works. Done. So based on the events generated using my keyboard corresponding to these keys, I can produce sound. So if I hit A, so this is the sound which comes. So if you're familiar with piano, this is the C major chord. This corresponds to A, D and G. A, D and G. This is the F major chord. The G major chord. You can actually change the patches to produce different sound. Now let me give it a control handle from the myRio device. I simply select this button, and when I use my device to perform some rotations, it sends the data wirelessly to this application, and it tries to figure out which of the events has happened and play the corresponding frequency. So if I select this patch, I rotate this, So you can very well hear how things are happening. So a different patch, selecting another different patch. I'm not sure if you can hear it. I can like use acoustic bars. I can select violin. Yeah, so this is for the demonstration. So let me stop this. Yeah, so this is it for the Air Music project. The entire source code for this project is available in GitHub, the link of which is provided in the description of the video. Also, good references are provided in the description. Thank you for watching this video.